Dear friends, welcome back. Yesterday we discussed about weight estimation by iterative process for electric powered propeller driven aircraft. At the same time we also discussed about how to perform, we started discussing about how to perform wing sizing. Right. So let us talk about that wing sizing in terms of planform geometry selection. So we want this UAV, which is of a particular weight, to fly at a particular velocity, right? So the whole idea during cruise is lift should be is equals to weight and the thrust, say acting in this direction, should be equals to drag, right? So if while calculating the thrust required, we assume it depends upon L by D, right, W by L by D. So if you know this information at what L by D you are going to fly, you will be able to figure out what is the corresponding thrust required. So when doing so, you also decide what is the lift at that particular, during that particular phase of flight, right. That means when you say lift, so you can also express the same as a non-dimensional parameter CL, which is 2 into L by rho S into V infinity square, right. So that means for this particular L by D, there is a particular, say this is your design L by D, there is a design CL. Right. So design CL is considered as an input while performing this wing sizing. So we need to design, say if this is my wing, we need to design this wing to perform this particular cruise, which is a major part of the mission, right. So during cruise, by the way, the weight of this wing is approximately 1.5 meters, 150 grams. And what is the span? Span, if you can see, is almost 1 meter span. It's a 1 meter span wing with a carbon fiber tube attached to it. Right. The whole setup weighs around 150 grams, and say it's a rectangular wing. You can see this is a rectangular planform, right. So what is the chord of this wing? And you can notice it's a symmetrical wing, right, with a symmetric cross sectional profile. The chord is approximately 23 centimeters, right. Okay, fine. So how much weight, or say the lift generated by this wing or this planform, what is the weight that it can sustain, right. So let us look into that. Let us try to see whether can we get that answer from this approach or not, right. So this half rho V square S into CL is equals to W, right. So S is equals to 2 times the weight of the UAV into density into V infinity square into CL design, right. So CL design implies V cruise, right. So V cruise is an input and the rho cruise is a cruise altitude, So generally the parameter W by S is known as wing loading, right. It decides the velocity of your cruise, all the velocities including takeoff, landing as well as cruise velocities. So selecting this particular parameter during this initiation of the design depends upon some conditions, like whether you want to design a hand launch UAV, or you want to design a UAV that take off with a short run up, or do you need a UAV or if you are going to design a UAV which has to run throughout the runway, like it will take a longer runway, longer distance for takeoff. So the type of UAV that you are going to design will help you to select the particular wing load, right. Say if you want to design a wing hand launch UAV, the W by S ratio will be from 7 to 4, right. It is in kg per meter square. Right. So this is in kg per meter square, right. So for a given weight where you can estimate the weight of the system, right, by just assuming the L by D, the weight breakup is already done, right. You know the design CL for the corresponding L by D, and you know what is the cruise velocity and the altitude from the mission requirements. You will be able to estimate what is the initial estimate of what is the planform area that is required, right. So once you have this planform area, how to get the planform geometric parameters? So what are the planform geometric parameters? For example, so we just measured the span of this wing, chord of this wing, and we decide, like we assume that this is a rectangular wing. Why? The chord at each point remain the same, right? It is of same length. Say at the root it is of 0.23 meters, even at the tip it is the same. But say if there is a variation at the root and tip, variation in the chord length at root and tip, then we call it as a taper wing, right. And then there can be a sweep and there can be a dihedral, right. The inclination of this wing with respect to horizontal is the dihedral, right. So these are the wing planform geometric parameters. So how to decide this? Right. So in this in this approach, we are going to talk about the wing planform geometry as a function of aspect ratio as well as taper ratio, right. So assume an aspect ratio or from historical database, right. So what is this assumption? Or you can say consider an aspect ratio. So how to consider? So this aspect ratio majorly classifies the UAVs into 3 different categories. One is acrobatic UAV, one is conventional UAV, or say which is of which is having a typical medium velocity UAVs, and acrobatic is one which has a higher velocity and higher maneuverability, right, and medium velocity UAVs as well as glider UAVs, right. So where you want a long endurance, higher endurance, that means you need the minimum power requirement. So the span should take care by itself, right. The span of the UAV should be sufficient enough to generate the lift at that particular altitude as well as the velocity, and that velocity should consume the minimum energy. So that means if we want to achieve a maximum endurance or the range, long range, right, so then you go for a design which is close to a glider. So long range UAVs are generally a glider UAVs, as well as long endurance UAVs are also glider UAVs, where they fly at very less velocity comparatively, right. So this aspect ratio classifies the type of UAV that you are going to design, right. So if this aspect ratio is anything greater than 15, you can consider it as a glider that particular UAV class belongs to a glider, right. So, for all those UAVs which are having aspect ratio beyond 15. So, anything between say 14 or 15 say till 8 can be a medium velocity UAVs, like, so their velocity of flight is higher compared to this UAVs, right. So, anything less than 8 is a low aspect ratio UAVs, right. So, we also witnessed, so acrobatic UAVs you can say, and delta wing UAVs, the aspect ratio will be less than 4, right. So, this classification you can figure it out from any of the conventional textbooks. Anyways, I will present a slide for this. Okay. Now, aspect ratio has to be considered as an input based upon the type of UAV you are going to select, and you have to iterate this aspect ratio, change this aspect ratio and figure out what will be the corresponding wing loading, right. And taper ratio. Is also an input from historical database. So, once you have this aspect ratio and lambda taper ratio, you will be able to figure out what is the planform geometry, major part of the planform geometry, right. So, what is aspect ratio? So, b square by s. So, corresponding span of the system will be, so now you have the span of the wing, yes, aspect ratio times the area, planform area or the reference area, and we have lambda is equals to Ct by Cr, right. And what is the planform area as a function of lambda and span? B by 2 into Cr into 1 plus lambda, right. So, what you have is Cr is equals to twice the planform area divided by span into 1 plus lambda. You will be able to identify or they have an initial estimate of the span of the wing, right. At the same time, by considering a lambda, you will be able to figure out what is the root chord here. Now, once you have the root chord, what will be the tip chord? Ct is equals to Cr into lambda. So, this particular parameter lambda will decide your tip chord as well here, right. So, you have the root chord, tip chord, span. So, these are good enough to calculate the mean aerodynamic chord, right. So, how to calculate the mean aerodynamic chord? Because ultimately we need to figure out what is the aerodynamic center of the wing, right. So, how do you figure it? So, that will be approximately 0.25 for a subsonic speed, like 0.25 to 0.23 to 0.26 of C bar for subsonic aircraft, right. So, C bar is equals to 2/3 Cr into 1 plus lambda square plus lambda. So, you can analytically estimate the C bar or the mean aerodynamic chord. With this C bar, you will be able to locate the aerodynamic center of this wing, right, approximately 0.25 times of this mean aerodynamic chord. So, another information that you require is taper, right. So, this taper is happening about a particular axis. You need to know the axis of taper. Should know what is the corresponding axis of your taper. Now, let us take a small example. Select the planform geometry of a delta wing UAV. weighs 3.5 kg, delta wing UAV to cruise at a velocity of 20 meters per second, 20 meters per second, right, and a design CL. So it is cruising at a design CL of 0.17, yeah, 0.177, design CL of 0.177. The aspect ratio should be 2.89. 8. So the aspect ratio should be 2.85 and a taper ratio of 0.167, right. So this UAV has to cruise at sea level, right? Consider sea level. Rho is 1.225 kg per meter cube. So this UAV has to cruise at this particular altitude, right, where the density is 1.225 kg per meter cube. Now we have to select the planform geometry of this. So first, to figure out the planform geometry, we need to know what is the area of the wing should be. Once you have the area, based upon this aspect ratio in lambda, we can figure out the planform geometry of it. W is equals to 3.5 kg, which is 3.5 into 9.81 newtons, 34.33 newtons, right? Okay. And CL design is equals to 0.177, and the corresponding velocity is 20 meter per second. So cruise velocity is given, density is given 1.225 kg per meter cube, right. Aspect ratio is given as an input, so b square by s is equals to 2.85, right, and taper ratio lambda Ct by Cr is equals to 0.167, right. Now let us figure out what is the area, planform area required to start with, right. For cruise, we have L is equals to W, so CL or half rho V square, V cruise square, density at cruise altitude of rho V square into S, reference planform area into design CL is equals to W. So the corresponding reference area is twice the weight divided by rho into V infinity square into CL, design CL. This equals to 2 times. So substitute these values, 34.33 newtons divided by 1.225 is a sea level density, since we are flying at sea level. So the corresponding velocity of flight is 20 meters square into CL design. What is the design lift coefficient? 0.177. So S is equal to 0.787 meter square. So this is the planform area that you require to lift this weight at this flight conditions, right. If you want to design a UAV of weighing 3.5 kgs, right, with this parameters or the performance parameters, you have to have an area of 0.787 meters square. So once you know the area, you can calculate what is the span of this UAV. So what is the span? Aspect ratio into S, because aspect ratio is B square by S, since ER is equals to B square by S. So this implies the span of this UAV should be 2.85 into S is 0.787. This implies the span of this UAV is 1.5 meters approximately. Okay. So this should be approximately 1.5 meter span, and the another information that you have here is lambda CT by CR. Okay. So we have area is equals to B by 2 into CR into 1 plus lambda. So CR is equals to twice the reference area divided by span into 1 plus lambda. So CR is equals to CR is equals to 0.9 meters approximately, which is twice 0.787 divided by 1.5 meters into 1 plus 0.167, right. So the root chord is 0.9 meters. So since we know the root chord, we can by using the definition of taper ratio, we can figure out what is the corresponding tip chord. CT is equals to CR into lambda, that is 0.9 into 0.167 is equals to 0.15 meters, right. You have CT, you have CR, you have the span, right. What will be the mean aerodynamic chord? C bar is 2/3 CR into 1 plus lambda square divided by 2/3 CR 1 plus 0.167 plus 0.167 square divided by 1.167. 0.614 meters is approximately 61 centimeter. S is 0.787 meter square, B is 1.5 meters, CR is 0.9 meters, CT is 0.15 meters, and C bar is 0.614 meters, right. So to start with, I have to draw 1.5 meters wing, right. This is 1 meter. This is half a meter. So I have 1.5 meter span here, right. So what should be the root chord for this? Where it should be? At 0.75. So this is your 0.75 of it. This is overall span is 1.5 meters, 0.75, and I have CRS 0.9. So assuming this is perpendicular, like this line is horizontal, and I made this face perpendicular to it, I have so this is my root chord, right. join the leading edge of root chord and the tip chord, all you have is a delta wing, right, of 1.5 meter span and CR of 0.9 meters, 0.15 meters of tip chord, right. So, since in the question it is mentioned it is a delta wing, we directly tapered it about the trailing edge here. Otherwise, we need to know the axis about which it is tapered, right. Okay. So, tapered is about trailing edge, that means the trailing edge of this root chord and the trailing edge of the tip chord should lie in the same, along the same line, right. So, this is the planform geometry and we will show the flight test of this particular design, particular UAV, right. Okay. Now, what should be the mean aerodynamic chord of it? What is the mean aerodynamic chord of this particular planform? So, we have C bar is equals to 2/3 CR 1 plus lambda by square by 1 plus lambda, that is 2/3. What is CR? 0.9 into 1 plus 0.167 plus 0.167 square divided by 1.67. This is 0.614 meters, right. This is 614 meters. Now, let us see what is this 614 meters. So, what is the mean aerodynamic chord? It is a chord at a particular location where your chord length is 0.614. So, where it is? Point 614 approximately. Okay. This is the mean aerodynamic chord in my case. So, in this particular case, this is the mean aerodynamic chord, which is which is 61.4 centimeters. Okay. This is a mean aerodynamic chord, right. So, similarly, you will have a mean aerodynamic chord this side. What should be the location of that? Y of mean aerodynamic chord is equals to B by 6 into this is 0.2857 meters or 0.286 meters is 28.6 centimeters, right. Is it? So, this is full scale, right. It should be almost equal to the same. So, see, it is approximately 28 centimeters from here, right. So, project this onto the root chord, project this MAC. Similarly, you will have mean aerodynamic chord this side as well, right. So, you project it onto the root chord. So, finally, this is going to be your mean aerodynamic chord. So, in this case, for a delta wing, since the trailing edge of root chord as well as the tip chord lies on the same line, right, you can easily locate the aerodynamic center. So, x AC is equals to CR minus of CT or C bar, right, CR minus C bar plus 0.25 C bar. What does it mean? What I am doing here? I am subtracting this mean aerodynamic chord from the total chord of this configuration or the root chord of this configuration, right. That means what you have is this length, right. So, plus I need to know what is the corresponding aerodynamic chord, I mean aerodynamic center for, so the aerodynamic center here is 0.25 of this C bar, that is a quarter chord of the C bar. So, this is my 0.25 C bar. So, what is 0.25 C bar of this? So, XAC with respect to C bar, right, is equals to leading edge of the C bar is 0.15 meters. that is 15 centimeters from here. A bit down, here it should be. So this is your, this is 15 centimeters, 0.15 centimeter. So 0.15 meters is from the leading edge of this C bar. Right. So to find out, so to measure this it will be difficult, right? You don't know physically where this C bar will present. So it is easy to mark this aerodynamic center with respect to the leading edge of the root chord, right? So what you need to do, you need to add this distance plus this distance, right? So to get this distance, you need to subtract C bar from the root chord, right? Say this is your C bar. Okay. Subtract this from the root chord, you get C bar minus CR minus C bar plus this distance. It's a quarter chord point of C bar. So this is going to be C bar minus CR minus 0.75 C bar. So this is approximately 0.4395 meters, which is 44 centimeters. Approximately 44 centimeters. So it should be, so you can simply have a tape and measure the corresponding mean aerodynamic or the aerodynamic center of this configuration, which should be approximately at 44 centimeters from the leading edge of this root chord, right? You can look at it physically, right? These are the two UAVs that we have just, with the same plan form what we have discussed. So one is a flat plate configuration, the other one is a reflex wing configuration. That means the profile is a rectangular cross section here for the first configuration, and the second one is with a reflex aerofoil cross section. The aerofoil that is used here is NACA 23110. Right? So let us witness the flight test of these two configurations.